shall talk about another type of instruments, which is called electrostatic instruments. Previously, you would recall that we have talked about electrodynamic instruments, and then the name automatically suggests that there must be something called electrostatic instruments, because there is something electrodynamic. So, why should there be not something called electrostatic? Okay. So, let us see the working principle of this instrument. This instrument is basically a set of a parallel plate capacitor. Parallel plate variable capacitor. Okay. So, it has a pair of parallel plates which may be like this. So, maybe I have one plate here, so this is one plate, okay, and say this is attached to a spindle which can rotate. Okay. So, this spindle can rotate on a bearing. So, this is bearing. Okay. And below this we have another plate which is like this. And let me bring these two plates a bit closer. Okay. So, and this plate, so this is not attached to the spindle. So, this second plate is not attached to this spindle. So, this is okay. Let me erase it from here. So, this is not attached to the spindle. This may be attached to the frame of the instrument. So, this is fixed, this is movable, and these two plates can have some common overlapping area, because this one can turn and this is fixed. Okay. So, let maybe I can demonstrate you this. So, we may go to the overhead camera. So let me take two plates. Let me make two plates, metallic plates. Although this is just paper now, but assume this is metal. And one of them is attached to a spindle like this. This can turn. And I have another plate which I hold in my hand, and this plate cannot turn. Okay, so one plate can turn, another cannot turn, and as it turns, you see the overlapping area between them changes. Here we have maximum overlap, here no overlap, okay, and here partial overlap. So this is the arrangement. Okay, so this is the arrangement. Okay, now what will happen if I apply, say, a voltage between these two plates? Okay, so now this is positive and this is negative side. So plus charge will accumulate here and minus charge will accumulate here. So this also acts like a parallel plate capacitor, and then these plus and minus charges, they will attract each other. So therefore this movable plate will try to come closer to this fixed plate due to attraction. And what kind of attraction? This is electrostatic attraction between two charged plates, electrostatic attraction. That's why this instrument is called electrostatic instrument. Okay, the previous instrument, which we call electrodynamic instrument, there the force of attraction was between a current carrying conductor. So there the charge was movable. Okay, so that's why that was electrodynamic force. Here it's electrostatic force. So then due to this force, this movable plate will come closer to this fixed plate, and if I now attach a spring as always to stop or to hold back this movable plate, then depending on the force of attraction, the amount of movement will be determined. Okay, so this is called electrostatic instrument. Once again, normally we would like to find out the equation or expression for torque. Okay, the idea here is once again very simple. The force or the torque, because they are proportional to each other, so the torque, which is proportional to the electrostatic force, is proportional to q square plus q minus q. The force between them is proportional to these two charges, is proportional to q square. And q, you know, this is given by, so you know that we know that the capacitance C is q by V, so we can write q is equal to, so this is proportional to V square. Okay. Therefore, if this voltage is V, then the torque Td will be proportional to V square, and the controlling torque, spring torque Tc, as always, is equal to k theta according to Hooke's law. So here if we write Td is equal to some k1 V square, the proportionality constant is k1, then we can equate Td equal to Tc at equilibrium. That means when the two forces are equal and opposite, cancelling each other. So then we can write Td equals K1 V square and Tc equals K theta. So theta will be K1 by K V square. So this is proportional to V square. Okay. So once again, theta will indicate V square. Okay, and or you can if it is time varying voltage, okay, or Vrms square for AC time varying voltage. Okay. Okay. Now one last thing that I would like to mention here, we will not prove it now, is the fact that Td, we have already said, is proportional to V square, and this proportionality constant is given by dc d theta half dc d theta. So this is the proportionality constant multiplied by V square. This is equal to Td. So we are not proving this expression now, but let us understand what it means, what this term dc d theta means. So we know that there is, so these two plates, these two parallel plates act like a capacitor. The two parallel plates act like a capacitor. Okay, and you can find the expression of the capacitance. C, this will be proportional to the overlapping area A multiplied by the dielectric constant of the medium divided by L. L is the distance between the two plates, where so we write A is equal to overlapping area and L is the distance between the plates. Okay. So this overlapping area A changes as this movable plate rotates. So we can write A as a function of theta. Okay. So A is a function of theta. Therefore, C is also a function of theta. As theta changes, overlapping area between them changes, and therefore capacitance also changes. If overlap increases, capacitance will increase. If overlap decreases, capacitance will decrease. Therefore, C is a function of theta, and therefore we can take a derivative of C with respect to theta, and this is the proportionality constant in this expression. Okay. So this is the meaning of this equation. We haven't proved this equation in this video, but we should understand the meaning of this expression. And maybe we can do a very quick exercise. So a small exercise. Say assume that that these are quarter circles. Okay, both these plates are quarter circles. So, total plate area will be how much? If this radius is r, okay, if this radius is r, then this area will be pi r square by 4. Okay. So, this is the total area and overlap. So, therefore, overlapping area will be so assume that theta equal to 0 is the position where the plates do not overlap, their edges are side by side. Okay. If that is the case, so theta equal to 0 is the position when we have one plate here and another plate here. So, exactly no overlap, 0 overlap. See, and then say this is fixed, this is movable, and this can move. So, this is the direction of theta, and I measure theta equal to 0 from this position. So, if so, then the overlapping area can be written as this total area multiplied by theta divided by pi by 2, 90 degree, because if it rotates by 90 degree, if this plate rotates by 90 degree, we will have full overlap. If it is 0 degree, we will have 0 overlap. Okay. So, then we can write this as this is theta r square divided by 2. Okay. So, therefore, now the capacitance C, which is equal to overlapping area theta r square by 2 multiplied by the dielectric constant epsilon divided by the length or distance between the plates L. So, this will be C, function of theta, and then d c d theta, this will be equal to, so this is linear in terms of theta. So, we will have r square epsilon by 2 L. Okay. So, this is very simple. So, here we have talked about this equation and we have tried to understand this equation, but we have not yet proved this equation. Thank you.